All right, so transverse and azimuth. Yeah, we did that right at the end. But it's, yeah, we started it right at the end. Good time to do it. Okay. So the idea with transverse and azimuth angles, right, we have, maybe we're given a vector. I was just working a problem in office hours. Wow. Where we had a vector that went down like this, okay? And the way we know it's transverse and azimuth is that usually there's kind of some dots like this, okay? And then they make a funny triangle. They have another dot that goes like this, and they give you both the angle here, which maybe we'll say that angle is, oh, I don't know, let's call it 30 degrees, right? And then an angle here that they call maybe 45 degrees, okay? So the way that we can tell that this is a transverse and azimuth definition of a vector is that they give you an angle that doesn't go to the vector itself, right? It goes to this intermediate kind of in the xy plane stuff. So that's your transverse angle, is that 45. The azimuth angle is the angle off of the xy plane. So in this case, you could call it negative 30, or you could just say 30 below the xy plane. Does that make sense? Yeah.
Say 95 or 45?
45. I'll make it pointier.
And you said the azimuth angle goes to the xy plane?
The azimuth angle is the angle off of it. It really doesn't matter whether you know which is transverse, which is azimuth. It just matters whether you can identify that this is not a coordinate direction angle problem, right? In a coordinate direction angle problem, it's possible that they might only give you two values, but they would be two values from an x-axis to the vector or from the y-axis to the vector. In this case, we have an angle that doesn't go to the vector itself. It goes to the projection of the vector onto the xy plane. So what we're going to do is we're going to break it into this guy, which lies in the xy plane, and I would call this typically f prime, right? So f prime is not at all what we're looking for, okay? It's a stepping stone to what we're looking for. When I break this into f prime, I would say that f prime is equal to f cosine of 30 degrees, right? So I'm taking this azimuth angle, or the angle off of the xy plane, and I'm projecting the force vector onto the xy plane, okay? At the same time, I would find the z component, and that's this piece right here, and that would be f sub z is equal to f sine of 30, right? Because it's the portion, it's the amount, it's the vector you would need to go in the negative z direction to end up here. Ultimately, what we're after, though, is we want to find what I'm going to call f sub x and f sub y, right? So f sub x in this case is going to be my value, or it's going to be f prime times the cosine of 45 degrees. Right? So it's f prime, because all f prime is this intermediate vector that lives in the xy plane. Okay? So it's a stepping stone vector. It lives in the xy plane. So when I find that value, then I multiply the magnitude of this vector times the cosine of 45 to figure out what this fx, which, I mean, that's the same vector as going along here. Right? There's f sub x. Then I'll do the same thing for f sub y. I'll say f sub y is going to be equal to f prime times the sine of 45 degrees. Right? So that's going to be this guy here. Right? Okay, so we could also say that f prime is actually f cosine 30 So then times sine 45. Does that make sense? The Middle East agrees with me. It's pretty awesome to be like all of the Middle East summed up in one person. You must have some serious indigestion, though.
You have no idea.
Sorry, I guess I shouldn't ever laugh about that. What's that?
I'm very oily too.
Very wealthy. Other questions? Does this make sense? Thumbs up, thumbs down? Medium. Oh, I see some tilting down, right? Okay. Let's do it again. Gonna do it again.
You should do it bigger so it's easier to see the graph.
Really?
Yeah.
Oh, bigger. Bigger, they say. I have to sound like Chewie when I do things big. Did you say I sound like a whale?
Dory whale.
Oh, Dory speaking whale. Oh. Okay. Where do I want to do my vector this time? What's my vector, Victor? Let's do the vector over here. Okay? And the key is you have to look at the dotted lines. Okay? Everyone see where that vector is?
Roger, roger.
It's in the positive x, positive z, negative x. Positive y, positive z, negative x. Right? Okay? So where would my, and we'll call this A for Andy. Okay?
Beautiful.
Thank you.
Just like him.
Oh, you make me blush. So where would A prime lie?
On that little shadow dotted line.
On the dotted line. Come on, guys. There's like 5 of them.
Essentially
The diagonal one, right? So we're going to say that A prime is right here. Okay? Is A prime any part of our answer?
No.
Not really, right? Because what we're after is finding A sub y, A sub x, and A sub z, right? So here's A sub z. And if I completed the problem by giving you some angles, right? So maybe this angle here, let's call it 20. And this angle here we'll call 30, right?
Is that A2 or AZ?
Z. So AZ would be what? What cosine 30?
A.
Mm-hmm. A cosine 30. Nope. Nope, definitely not cosine. Sine 30. Right?
Andy,
Yeah.
is that 30 degrees between A prime and A?
Yep.
Okay.
But more importantly, that's not what they're going to tell you in the problem. They're going to say that that 30 degrees is between the xy plane. That's the azimuth angle. So it's 30 degrees. I mean, think of it about, the only way I know to think about it is think about shooting a giant gun off of a boat, right? And they say, come about, right? channel all my Hunt for Red October, come to 30 degrees, and then azimuth up 20 degrees. It's the opposite in this case, isn't it? So I just dorked it up. Come about to 20 degrees, and then azimuth up 30. Right? So one angle says in my XY plane, where am I? The other angle says how far off of that plane am I, right? Does that make sense? Okay. Yeah, put a shot across their bow. Okay. All right, so that's AZ, what do I get for A prime? How do I find A prime? Cosine 30. A cosine 30. All right. And then how would I find AY? Say that again, Max. A cosine 30 cosine 20. Right? Because this here is just giving me A prime. Right? A sub x, I'm going to do it over here. A sub x is going to be A cosine 30 sine 20. And again, this is just A prime.
When you write A, you mean like the vector A?
I mean the magnitude of it.
Okay.
Yep. How are those thumbs doing? All right. The vector's positive, Victor. Yeah, Rebecca?
Can you explain one more time how it is that you can get A sub x by doing A prime times the sine of 20?
Yeah, because A prime is just this vector. What we're doing is we're working backwards from my gunship, right? So here we're saying, boom, there's A, right? And then I say A cosine 30 brings me down. That projects me down to the XY plane. But then I need to figure how much of it is in X and how much of it is in Y. So then I take the cosine of 20 and the sine of 20. All right? Okay. Other questions from the homework? How many people did problems besides the graded problem this weekend? Was that I really thought about it, but then I didn't? Was it? I'm just curious what this... You tried it? Okay, so you did one. All right, that's good. All right. Okay, so... Okay. So, let's jump into position vectors. Y'all have done position vectors in other classes, likely? Okay. Probably you have. Okay, so a position vector, I'm just going to show you, we're not going to spend a lot of time on this because I think you'll get it fairly quickly. We'll often have, say, this point out in space B. Okay? And B will say, to get to B, you travel in the X, Y, and Z directions. And B that's where B is. Okay? So in Hibbler, he always uses the letter R, little r, for position vector. Okay, so this is a position vector, and we could say RB in this OB. And what that means is that the position vector from O to B, or the position of B with respect to O. Okay? And this is going to be really important, not so much in statics, But in dynamics, it becomes really important. So let's just start now thinking about them the same way. So the first letter in the subscript is where you start, and the second letter is where you end up. Okay? So this is R, O to B. Does that make sense? So that means it's a vector that goes from the origin here, O, out to B, like that. Okay? And if B has coordinates something like -3, -5, or excuse me, +5, and 2, right? We can pretty quickly come up with the position vector R, O to B. And the way we do that is we say the x position of B minus the position of the origin in the I hat direction plus the x position, or excuse me, the y position of B minus the origin, which is 0, j hat, plus the z position of B minus 0, because it's at the origin, k hat. So R, O to B just becomes -3 I hat plus 5 j hat plus 2 k hat. Okay? Does that make sense? Everyone good with how to figure out the position vector of B? So let's say I have another point right here that I'm going to call A. And A is located there. So A has the coordinates of, let's say it's 2, -2, -1. Right? So it's +2 in the x, -2 in the y, -1 in the z. Okay? And maybe I want to figure out the position vector RAB. Okay? Someone tell me in words, where is RAB starting and going? Starting at A, going towards B, right? So I'm going to start here, and I'm going to go to B. So it's unfortunately going to end up right on top of my other vector in the picture. Is it actually on top of it? Probably not, right? I don't think I'm that lucky at picking numbers. So again, what I'm going to do, RA to B, I'm ending at B, so I'm going to take the value of B, which is -3, okay? And I'm going to subtract the value of A. Did I just dork this up? Should make it -2 and +2. Nope, I'm good. Okay, so this is A in the x, excuse me, B in the x minus A in the x, I hat, right, plus 5 minus -2, that's B in the y minus A in the y, j hat, plus 2 minus -1, k hat, because that's B in the z minus A in the z. So we'll end up with RAB equaling -5 I hat plus 7 j hat plus 3 k hat. Right? Everyone okay with that? All right? So then what's R, B to A? Just change all the signs, right? Just going the other way, so it's opposite. Okay? So I'm going to put C on here. And C is going to have coordinates -3, -2, 3. And I'd like you to find me R, BC. Okay? So take a minute and find RBC. For our video audience, I did not record for the last 10 minutes, so there's some stuff. Here's some more stuff, and we'll talk about it in class. Sorry about that. So we're talking about unit vectors here. We would not typically take this position vector, RAC. We need to figure out how this would have a magnitude of 1. What is the magnitude of this vector right now? Root of 25, which is 5, right? So the magnitude of this vector is 5. We know that right now. So if I multiplied 200 pounds times this, I'd be actually multiplying it by a factor of 5, right? I don't want to do that. Anyone have a suggestion for how we should find the unit vector? Divided by the magnitude, right? So if I take this, remember I just said if I multiplied 200 pounds by this vector, I'd be multiplying its magnitude by a factor of 5, right? So if I don't want to do that, if I want to multiply it by a factor of 1, I would just make this 1/5 the size that it is. So I'd multiply my position vector by 1/5 or by its the inverse of its magnitude, or divide it by its magnitude. Okay? It's a different way to think of how we come up with a unit vector. All I'm going to do is going to take its magnitude of 5 and divide it here. So the unit vector AC is just RAC divided by its magnitude. So it's going to be 4/5 in the I hat direction plus 3/5 in the J hat direction. Okay? The unit vector of BC is same thing, -4/5 I hat plus 3/5 J hat. All right? Yes, sir.
Now, can you divide vectors like that? We were told that you have to multiply it by something. You can't actually divide it.
So I can multiply it by 1/5,
Right.
which is dividing by 5. So
Yeah.
I'm not sure what they mean by you can't divide. But.
Yeah, they were just very stickler on don't ever have a divide in a.
Yeah, you're gonna find that I'm not super sticklery on things like that. So.
Because you're not dividing the whole vector, you're just dividing the components.
That's true. I'm just that's a good point. I'm just dividing the scalar magnitude in the I and the J direction, right? Okay, so now that I have these, watch what happens. I can multiply. I have this magnitude of 200 pounds, right? So we know that FAC, not a vector, right? That's just the scalar magnitude, is 200 pounds. And I know that FBC is just 200 pounds. Okay? Or I guess I didn't say that, but I'll say it now. All right? 200 pounds in each of those ropes. So if I multiply this, these don't currently have direction. So this is like me trying to walk around with gravity moving all over the place. Bad things are going to happen. You have to give a force direction. So let's give it direction. By multiplying it, we know it acts along that rope, right? So we're going to multiply it by that unit vector that we just came up with. It gives it direction but doesn't change its magnitude, okay? So when we do that, 200 times 4/5, I'm pretty sure that's 160 I hat. And times 3/5, What's that? That'd be, oh gosh, 120. Thank you. Plus 120 j hat pounds. Okay? And if I do that down here, I'm going to multiply FBC by its unit vector, UBC, right? Then I'll have minus 160 I hat plus 120 j hat pounds. Okay? What's interesting now is I could take the resultant, or I could ask what's the resultant of these two forces, and we'd see it's 0 in the I hat direction plus 240 in the j hat direction. Which is good, right? Because if we're lifting something up with a crane, it's probably just counteracting gravity, and so this thing is holding up that beam. What does the beam weigh? 240 pounds.
Whoa.
Okay? Does anything bother you about this?
Yeah.
What?
Where's that extra 40 come from?
Where's the what?
Where's the extra 40?
The extra 40.
Pounds.
Oh, the extra 40 pounds. So we have 200 and 200, right? But the deal is that they're kind of almost going horizontal. Or no, they're not going horizontal, but they're not as efficient because the force vector is going up, and these guys have to pull really hard horizontally to get that up force.
That'd be better to have like.
So there's really 400. So Sean said what bothers him is that there's this, that it's 240 when we just had 200 and 200. And I would say, actually, I understand what you're saying. You're saying, where's the extra 40 come from? What I would respond back to is, where'd the other 160 go? Right? Because we had a total of 400 pounds of force acting. Everyone see that? We had 200 pounds on the left and 200 pounds on the right, which to me says 400 pounds. But we end up that the beam only weighs 240. Why? Because only the z components, or in this case the j components, since I'm just using x, y, are acting in the positive x direction, and then in the in the positive y direction. In the x direction, it counteracts itself. It's pulling against itself. Yeah.
So does this mean there's like 240 pounds on the crane, or on like the hook?
Yep, on the hook.
And 200 pounds each on the rope?
Yep. So what this means is that if I looked at the tension in the cable on the crane, I'd find 240 pounds. And if I looked at the tension in the ropes here and here, I'd find 200 pounds. Okay? So you don't really need to worry about this so much. That's actually chapter 3. But we're introducing the concept of a unit vector, which is really important. I think this is a very simple way to say, look, I have 200 pounds going in this direction, but I don't really know what that direction is. How can I tell you what it is? Well, I can figure out my position vector. From my position vector, I can figure out the magnitude of that position vector. And then if I multiply, or if I divide the position vector by its magnitude, I'm going to end up with a unitless, or magnitude 1 unit vector. Okay? It would be unitless as well, but it just has a magnitude of 1, and it communicates only direction. Okay, so let's try it. Let's go back up to where we were doing position vectors, right? Engineering 211 is filmed before a live studio audience. We found all these position vectors for A to B and B to C, right? So our position vector, RBC, we found here as being 0, I, -7j, and 1k, all right? What would its unit vector be? If I want you to find me UBC, how do I do that? What do I first have to do? Find the magnitude. So the magnitude would be 7 squared, 49, plus 1 squared, that'd be a total of 50, and then take the square root. So it'd be root 50. So the unit vector of UBC is 0I minus 7 over root 50j plus 1 over root 50k. How about RAB? The magnitude of RAB is going to be 5 squared, which is 25, plus 7 squared, which is 49, so 60, 74, plus 3 squared, I think that gets me 82. Someone check that? Don't all jump to your calculators at once.
83.
83, I was off. Okay, so then if this is root 83 is going to be its magnitude, so then I could say that the unit vector AB is going to be negative 5 over root 83 I hat plus 7 over root 83 j hat plus 3 over root, oh my gosh, this is getting ridiculous, plus 3 over root 83 k hat. Right?
The reason for the unit vector of B3 for the I and the J, those don't have hats.
They all should have hats.
Gotcha.
Yep. Okay. I, J, and K always have hats in this class. All right. Any questions on unit vectors? Okay. I'm going to carry on. I want you to do some of those, okay? So I want you to do some problems out of 2.7 and 2.8 because it's going to be really important. The last thing we need to talk about is the dot product. Nah, I can't. You have to do it. We have to do an example before I can go on to the dot product. So let's look at all right. We'll look at F21. Okay. Let me see if I can freeze us so you can get that in your notes. It gets fuzzy typically. I can try. Is that okay? Still fuzzy, but better, maybe? I don't know.
Good enough.
Good enough? Come on, Mr. Computer. Okay. So we have a force vector. Looks like it's 630 newtons. It comes out of the xz plane at 2, 2, okay? And it goes down to B, which looks like it has coordinates 4, 3, negative 4. And we need to express this vector as a Cartesian vector, okay? So I'll let you go ahead and draw that for a second, and I'll draw it in my notes. Is 3, 4, negative 4. It's 4, 3, negative 4, sorry. Yep.
Much more logical.
Yeah? Okay. So let's start with our position vector. The force is going from, I don't know what they labeled it, but I'm going to label it A and B, RAB. Our position vector is going to be from A to B, right? So we take the end point and we subtract that coordinate from the beginning point. So in the I hat direction, I have 4 here and I have 2 there. So I'd have 4 minus 2 I hat. Plus, In the y direction, I have 3 minus 0. And in the k hat direction, I have negative 4
The president's calling.
he does that all the time. Okay. Negative 4 minus 2 in the k hat. Right? So RAB.
You're outside of your box.
How am I outside? Oh, sorry. There you go. This is going to be 2 I hat plus 3 j hat minus 6 k hat. So the magnitude of RAB that's beautiful. 2 squared, 3 squared, 6 squared. Okay?
Where did you get the 4 from?
Right here. It's 4 in the x. And then it's 3 in, yeah. I always get those backwards too. So it's 4 plus 9 is 13, plus 36 is 49. So I'm actually going to want to square root this and square root that, and I end up with 7. 7 is what? What is 7? It's the magnitude of the vector, right? Okay. So then the unit vector for AB is going to be 2/7 I hat plus 3/7 j hat minus 6/7 k hat. So if I want the force vector, FAB is going to be 630 times the unit vector AB, or 630 times 2 over 7 I hat plus 630 times 3 over 7 j hat plus 630 times negative 6 over 7 k hat. Okay?
What notation are you using for unit vectors? Are you just using a U?
Yep, U and then the subscript of where it's going, A to B.
Can we just put RAB with a hat instead?
Nope. Nope. Okay? All right, so I want you to do a chunk of problems out of 2.8. Do them until they're really mind-numbingly easy and boring. Okay? Because you're gonna you're gonna have this skill for the rest of the class, big time. Okay? So when we come back in on Friday, you should have these nailed. We'll do hopefully 20 minutes on the dot product, and then we're gonna get into chapter 3 on Friday. All right?